This is the review for Chapter 9 test part 2, starting with number 12. On page 596, number 35, you're given the force vector and you're given a second vector that starts at 0, 0 and goes to 3, 8. We want to find the work done. Well, the formula for finding the work done on an object is the force vector times the distance vector. Well, I know the force vector, I got to find the distance vector. I'm going to find the distance vector by using these 2 points. Remember, it's terminal minus initial, terminal minus initial. Now I can perform the dot product on the force and the distance. So the force vector is 4, negative 5. The distance vector is 3, 8. I'm going to get 12 plus negative 40, which is going to be negative 28. Now, we don't usually say work is negative, so we would actually just say the work is 28 foot-pounds. We found out with working with vectors in 3 dimensions that they work pretty much the same as vectors in 2 dimensions. In order to find the magnitude of this vector on page 608, number 11, all you have to do is, write that first, negative 2 squared plus 1 squared plus 2 squared. So that's 4 plus 1 plus 4, which is the square root of 9, which is 3. On page 609, number 37, we're given the vector 3i plus 4j plus 5k in 3 dimensions. To find the direction angles alpha, beta, and gamma are the degrees from the x, y, and z axes. So the cosine of alpha is going to be the first component divided by the magnitude of the vector. The cosine of beta is going to be the second component divided by the magnitude of the vector. And the cosine of gamma is going to be the third component divided by the magnitude of the vector. Alpha is the degrees from the x-axis, beta is the degrees from the y-axis, and gamma is the degrees from the z-axis. So I need to know 2 things. I need to know what A1, A2, and A3 are. Well, that's easy. This is A1, A2, A3. But I also have to find the magnitude of the vector. So the magnitude of the vector is the square root of 3 squared plus 4 squared plus 5 squared, which is the square root of 50. So to find alpha, we're going to do the inverse cosine of A1 was 3 over the square root of 50. And just be careful how you plug this into your calculator. You're going to get 64.9 degrees, or approximately 65 degrees. To find beta, we're going to do the inverse cosine of 4 over the square root of 50, which is approximately 55.6 degrees or 56 degrees. And gamma is going to be the inverse cosine of 5 over the square root of 50, which is approximately, no, actually it's exactly, try that again, 45 degrees. In number 15, page 609, number 27, we are given 3-dimensional vectors u and v, and we want to find the dot product. Remember, this works like the dot product in 2 dimensions. The only difference is I have to deal with 1 more set of numbers. So I multiply the x components together, plus the product of the y components. And then all I have to do is add the product of the z components. Just remember that the answer to a dot product is a scalar. So I'm going to get 5 plus negative 6 plus 2. And the answer is going to be 1. Number 16, page 608, number 5. When you have 2 points on a vector, you have the initial point and the terminal point, you find the vector in exactly the same way. You'll just have 3 components. So vector PQ is going to be 0 minus 1, comma, negative 2 minus negative 1, comma, 5 minus 0. So it's negative 1, 5. If you want to write that in IJK form, you would have written negative I minus J plus 5K. I don't care which form you write it in unless I specify on the test which one to give me. Number 17. In 3 dimensions, we can add, subtract, perform scalar multiplication on these vectors just like we did in 2 dimensions. Be careful though. I want you to notice that there's a missing 0K here in U, and there's a missing I in V. So when I go to add these 2 vectors, I have to add 1 plus 0, 1 plus negative 1, 0 plus negative 2. So the first vector is either 1, 0, negative 2, or I minus 2K. When you subtract them, 1 minus 0, 1 minus negative 1, 0 minus negative 2. So you can either write this as 1, 2, 2, or as I plus 2J plus 2K. In order to do 3U minus 1/2 V, I'd first find 3U, and I prefer writing it in component form. So I'm going to do, it's going to be 3, 3, 0 minus 0, negative 1/2, negative 1. Now I'm going to subtract these 2. So 3 minus 0 is 3. 3 minus 1, negative 1/2 is going to be 3.5 or 3.5. And 0 minus negative 1 is going to be 1. Number 18, page 615, number 7. The cross product, unlike the dot product, is going to result in a vector answer. In order to do the cross product, we're going to use a determinant in 3 variables, or of order 3. Remember, the way this works is I, J, K is the first row of this matrix. The second row comes from vector A. It's going to be 1, 1, 1. And the third row comes from vector B. 3, 0, negative 4. We're missing a J, so it must be 0J. Alright, the way that the cross product works is first you're going to do I times this determinant, and then you're going to do minus J times this determinant, plus K times this determinant. The determinant is done in a very particular fashion. You have to specifically multiply this first minus this. Multiply this first minus this. Multiply this first minus this. And then simplify. So I get negative 4I plus 7J minus 3K. This is the value of the cross product. And again, I said it was going to be a vector rather than a scalar, like when we do the dot product. Number 19, page 615, number 25. I want to find the area of triangle PQR. We found out that one of the ways we can do this, when we're working with points in 3 dimensions, if we can find the vectors, we can find the area of a parallelogram by doing the cross product of the vectors. To find the area of a triangle, you would do the same thing. You would start by finding the cross product of the vectors, finding its magnitude, but then multiplying that by 1/2 because you know that a triangle is 1/2 of the value of the area of a parallelogram. So the first thing we're going to do is we're going to find vector PQ. P is our initial and Q is our terminal. So vector PQ is going to be -1, 1, -1. Then I'm going to find PR. PR is going to be 1, 3, 3. Once I know PQ and PR, the next thing we're going to do is find their cross product. So I'm going to have I, J, K in the top row, -1, 1, -1 in the second row, and 1, 3, 3 in the third row. I'm going to start to skip steps when I do this, so pay close attention. The first term is going to be I times this determinant. It's going to be 3 minus -3. Minus J, I'm going to use the determinant of these. So it's going to be -3 minus -1 plus K. I'm going to use the determinant of these four. So it's going to be -3 minus 1. Now I'm going to simplify, and I'm going to get 6I plus 2J minus 4K. Now that I know the vector, in order to find the area if this were a parallelogram, I'm going to find the magnitude of that vector. So now the magnitude is going to be the square root of 6 squared plus 2 squared plus -4 squared. And I'm going to find out that that's the square root of 56, or 2 the square root of 14. Now this is what the area would be if it was a parallelogram, but it's not a parallelogram, it's a triangle. So in order to find the area of the triangle, you're going to take 1/2 of that answer. Well, I'm going to find out the answer is just the square root of 14. Number 20 is from page 588, number 54. A jet is flying in a direction north 20 degrees east with a speed of 500 miles an hour. Find the north and east components of the velocity. First of all, let's remember that north 20 degrees east, here's my coordinate plane, x, y. This is north 20 degrees east. But 20 degrees is not the angle that we're going to use. We're going to use 70 degrees. So now, in order to find the north and east components, which is the same as the vertical and horizontal components, we're going to do 500, because that's the magnitude of the vector, cosine of 70 degrees. That's going to give me my east component, or horizontal component. And then I'm going to do 500 sine of 70 degrees, which is going to give me my north, or vertical component. So 500 times the cosine of 70 is 171 approximately. And 500 times the sine of 70 is 469.8. This is my east component and my north component. Number 21, page 596, number 31. Given vectors u and v, I want to find the projection of u on v. The projection of u on v was a vector that lied on top of another vector, as opposed to the component of u on v, which was a scalar quantity on top of a vector. To find the projection of u on v, we do the dot product of u and v, divide it by the square of the magnitude of v, and then multiply that by vector v. That means that my final answer is going to be a vector. So first, u dot v is going to be 1 plus negative 6, which is negative 5. The magnitude of v is going to be the square root of 1 squared plus negative 3 squared, so it's the square root of 10. But we're going to square that when we plug it into the formula, so when you square a square root, they cancel. So you're left with negative 5 over 10, which is negative 1/2, times vector v. So we're going to find out that the answer is negative 1/2, comma, positive 15 over 10. That's the projection of u on v. If I want to break that into components, u1 is always the projection of u on v. So we found out that that was negative 1/2, comma, 15 over 10. u2 is vector u minus the projection of u on v. So if I subtract the original vector 1, 2 minus negative 1/2, 15 over 10, I'm going to get 1 and 1/2, or 3/2, or 1.5, and then 2 minus 15 over 10 is going to be, let's see, it's going to be 20 over 10, which is 5 over 10, which is 1/4. And that would be u2 if I broke it into vectors u1 and u2. Last problem, page 597, number 50. A car is on a driveway that is inclined 10 degrees to the horizontal. A force of 490 pounds is required to keep the car from rolling down the driveway. Find the weight of the car. So here's the driveway. It's inclined 10 degrees. Here's the car. There are 3 forces here. We have the force that keeps the car from rolling down the hill. We usually call that U. The force perpendicular to U, which is the force of the car onto the hill, we call that V. The third vector, the one pointing straight down, is vector W, and that has to do with the weight of the car. Problem is, I don't know the weight of the car, but I'm going to find it because I could find the weight of the car doing the component of W on U. That means it would be the magnitude of the weight times the cosine of the angle between these two. The angle between U and W is not 10, it's 80. The magnitude between V and W is going to be 10. It's going to be the same as the inclination of the hill. Well, I know that that better equal the magnitude of U. So I'm going to solve that equation for W. So I'm going to divide both sides by the cosine of 80. And I'm going to find out that the weight of the car is approximately 2,822 pounds. Now that I know the weight of the car, I can do the second part of the problem, which is to find the force the car exerts against the driveway. In other words, I want to find the component of W on V. Alright, so I need to know the weight of the car, which is 2,822, and we're going to do the cosine of the angle between V and W, which I said is the same as the inclination of the hill. So 2,822 times the cosine of 10 degrees is going to be 2,779 approximately pounds. Whenever you're finding the force exerted by an object on a hill, the answer better be less than the actual weight of the vehicle. And that is the end of the review for part 2.